I guess we're gonna wait for other people to show up. Let's just give it a minute for other people to show up for the class. So you guys, I graded the quizzes and the homeworks and the classworks and posted all those things onto our grade portal. If you should be able to access those. So if you can't access your grades or see the comments that I have made, because like, you know, there's like, I can load it up on my screen and I can make comments on it. It's all electronic on my screen. If I make comments on that, you should be able to see those, okay? In addition to like the grades, like the points taken off and stuff that I've put on there. If you can't access those grades on there on the grade portal, please send me an email or let me know in the chat, say, for example. And then that way I can contact IT or figure out like what's going on or why that isn't working. I'll just make sure that those are there. Let's see, I think, why don't we, we'll give it like another minute, see other people are going to show up and then we can go ahead and get started. But don't forget, we also have a quiz coming up this week as well. It's on chapter 1.3 and 1.4. Okay, so those homework sections will be due this week. So keep that in mind for things that are coming up. The quiz will be the same format that we did before in terms of availability. So it'll be available Thursday afternoon at noon until Friday afternoon at noon. So you'll have essentially a 24-hour window within which to take a look at it. If for some reason you didn't take the quiz from last week, please send me an email as soon as possible. We need to arrange a makeup quiz for you. So please contact me about that. Okay. All right. So last week, let's go ahead and get started. So last week we were talking about chapter 1.4, where we ended off with, and this was our cross product. Okay, so this is just a remembering where we left off. Okay, so cross product, remember, takes in, we've got two vectors, and these are three-dimensional vectors. Okay, they've got an x and a y and a z component. And then our output for our cross product, and we get one vector that is perpendicular or normal, orthogonal. All these things mean the same thing. Perpendicular, normal, normal is what we usually call our vectors, normal or orthogonal to the two input vectors. This is important, right? We think about, we have V1 and V2 as our two vectors. They're not parallel to each other. Hang on a sec. Our two vectors are not parallel to each other. And then the output that we get is a vector that's perpendicular to both. So we typically call that, oops, no way. Okay. So, that output is normal. We call it N for normal, okay? And this becomes important. So let's, I want to talk about a couple more properties for our cross product. I don't know why the delayed getting into the meeting. Okay, so let's talk about some other properties, and then we'll go into a final example for 1.3 and 1.4, and then we'll break for a little bit and work on some of the classwork problems for 1.3 and 1.4. They're pretty important. I think we just focused on 1.1 and 1.2 last time. I want to talk about classwork for 1.3 and 1.4. And then, and if we have time today, we'll start on chapter 1.5. But I want to make sure that we're all on the same page about 1.3 and 1.4. Okay, so let's talk about some other rules or properties of the cross product. So remember, our cross product is a way to do multiplication of two vectors. So we did a scalar multiplication of a vector, which meant I'm just going to multiply my components, my vector components, by a number, by just a regular number. If I want to multiply two vectors together, I either do a dot product or I do a cross product. Remember, they have different outcomes and different reasons for why you would want to do those. Okay, so let's think about it. So one of the properties is, and we kind of touched on this a little bit. V cross W is not the same thing as W cross V, okay? So what happens is, if I want to do V cross W, this is actually equal to negative W cross V. And what that means, remember, we're getting a negative. It's a vector that we're getting as an output. This comes from our geometry. So think about our geometry of our vectors and what that means to have like the right-hand rule and what's a positive or negative vector mean. So if I've got, so here's W and here's V and here's the angle between them, my direction of cross product taking, here's our direction of the cross product, right? So I'm going to go V cross W. You can think about it as my right-hand rule. So I'm going to go, I've got W and I've got V. I'm going to cross V towards W. So I'm going this way, right? My right-hand rule. I'm going to get a vector that points up. Okay, so I do the right-hand rule. This is my right hand. I don't know if you can see that in a zoom window or flips it. This is my right hand, and I'm going V cross W. I get a vector that goes up. Some books, when they talk about the right-hand rule, they say, like, you know, you're making a V with your fingers, but split them apart like this, and then stick your thumb up. It's hard to see it on the screen here, right? But I'm basically looking at, I've got V and W, and then I have a vector that points up. Up is arbitrary, but we're gonna do it like this. So that's my direction, like this, okay? So now, let's say I have W cross V, right? So this is our direction of cross product. This is W cross V. So now what happens, right? I'm going in the direction. So I'm going to go W to V. So I'm going in this direction here, right? So I'm going my right-hand rule. I'm passing it this way. I'm going to get a vector that points down. So here's my WV. They go this way and they point down. Okay, so that means the vector that I get points this way. This is a negative, right? So if N, we think about it this way, this is my negative N pointing down this way. It's still perpendicular to these two vectors here, okay? But it's pointing in the opposite direction. Okay, so you're still gonna, if I take the magnitude, like if I do it, I want to calculate the magnitude or the area of my parallelogram, the area of my triangle, I'm taking the magnitude. So it doesn't matter if I go W cross V or V cross W, because I take the magnitude and I get like a positive number. My magnitude's positive, okay? But in terms of when I want to think about V cross W, make sure that you're thinking about that. I'm going to get a vector that points up this way. Okay, so this is our geometry. I'll put that as property number 2. Property number 3 that I want to talk about is if A and B are scalars, and then P and Q are vectors, right? And if I do this, we can say P cross AQ plus VR. Okay, oops, PQ and R. There's an R in there. Those are vectors. Okay, so now what happens, right? If I distribute this along here, right, what this is going to look like is this. It's going to be A times P cross Q, right? It's a scalar multiple, okay, of the vector that I'm getting after I do this. Okay, plus B, right? So I'm going to do this, P cross R. So watch our direction here, right? It's P cross Q plus P cross R, and I have a scalar multiple. The scalar multiple is still going to be the same scalar multiple, right? It's the same thing as though I were to multiply A times every component of Q and then take the cross product. Okay, B times every component of R and then take the cross product with P. I'm going to get the same thing as though I were to take the cross product and then multiply. Same outcome, okay? This is what we get here. So this is, but watch the order, okay? So now, if I put the cross on the other side, so let's do it like this. AQ plus BR cross P, right? Remember we said about the order being important. Okay, so this is one of them. This is going to equal to A times Q cross P, right? Watch the order. So I'm going to go Q cross P. I kept it in that same order. Plus B, right? And watch what's going to happen. Yeah, B is my scalar. R cross right? So I have to be very careful about my order on things, right? Because my, this, I'm gonna get a scalar times a vector plus a scalar times a vector. This is our linear combination, right? Linear combination of vectors. Okay, so think about that. Okay, so these are just some properties that we were talking about with vectors and cross products. Okay, so our last example, example 4, is kind of a mega example, has a lot of different pieces to it. So we're just going to take it from the top and work our way through. Okay, so example 4 says I've got these 3 points, 1, 0, 1, 2, 1, minus 1, and 0, 3, 0. And then I want to find out what's the vector equation for the plane containing the 3 points. What's the area of the triangle, which has A, B, and C as my vertices? And what's the angle between the 2 displacement vectors using A, B, and C as reference points? Okay, so there's a lot of different pieces that are happening here. So let's take it piece by piece. So part A, okay, so what's the equation for the plane? So this is the vector equation for the plane. We're going to learn in chapter 1.5, we can have a non-vector equation, sort of like an x plus y plus z equals. So we're going to talk about now a vector equation for the plane. Remember, is x bar, which is equal to x naught. This is our point plus our first parameter times our first vector plus our second parameter times our second vector. Okay, when I'm dealing with the plane, I have 2 vectors. Okay, these are displacement vectors between my points, and I need 2 parameters, and I have a point for reference. Okay, so this is my plane. So I'm gonna, draw this out like this. Here's my plane. Now the planes are infinite planes in all directions, unless we put restrictions on T1 and T2, but you can conceptualize the planes are infinite planes. I can't draw infinite planes, so I kind of encapsulate it as though it were, this plane right here. So I've got A, B, and C as 3 points on my plane. Randomly, I'm going to choose A as my initial point, and I'm going to calculate my displacement vector, V1, as being between A and B. I'm going to choose A and C are the 2 points that are going to help me calculate my displacement vector for V2. It doesn't matter. You can use B as your initial point and then calculate your displacement vectors from B to A and B to C. Or likewise, you can do C as your initial point and then calculate displacement vectors from C to A and C to B. It's totally up to you. You're going to get the same vector values, but they may be in opposite directions. Okay, so I just chose it this way. All right, so let's write out x naught is a point on the plane. Okay, that's our initial point, which we chose to be A because that's the point that we're using as our reference point. So that's going to be 1, 0, 1. Okay. And then I need to calculate V1. This is a displacement vector. Now remember, displacement vectors are terminal minus initial. Terminal point minus initial point. Okay, I can't just choose one of the points that I want and make it a vector. It has to be, I'm going from this point to this point. I have to choose, this is my initial, this is my terminal, terminal minus initial. Okay, so V1 we said was going to be, I'm going to go A to B, which means A is my initial, B is my terminal. So I'm going to put B. So 2, 1, minus 1, minus my A, 1, 0, 1. Okay, so this is going to be 2 minus 1. 1 minus 0, minus 1 minus 1 is minus 2. Okay, that's my first vector, V1. Okay. My second vector, V2, this is a displacement vector. Okay, and so V2, we said we're going to go from A to C. Oops, sorry, I wrote B. Sorry about that. Fix that. A to C, okay, which makes A my initial point, C my terminal point. So I'm going to go, this is going to be C minus A. So this is going to be 0, 3, 0, minus A, 1, 0, 1. Okay, so 0 minus 1, 3 minus 0, 0 minus 1. And this is V2. Okay, so now I have a point on the plane. I have a first vector, second vector. I can just plunk them down into these spots on my vector equation for the plane. Okay, so my vector equation for the plane is going to look like 1, 0, 1 plus T1 times V1, 1, 1 minus 2, plus T2 times V2, minus 1, 3 minus 1. And that's my vector equation for the plane. Okay. Remember, I had to calculate my displacement vectors in order to do that. Okay. All right. Now, B, part B says, what's the area of the triangle that's spanned by, has the vertices A, B, and C? Oops, sorry, you can't see that. A, B, and C. Now remember, we did, this is V1, this is V2, and then we just have this line here that forms the other, you know, arm of our triangle here. Okay, so I'm going to calculate out that area of the triangle. So now remember, if I think about this as a parallelogram rule, I'll draw this out in a different color. If I do my parallelogram rule, I've got, this is going to be V2, this is V1. Here's my parallelogram rule. This is the diagonal between them, right? So the area of the parallelogram excuse me, is equal to the magnitude of the cross product, right? This diagonal cuts my parallelogram in half. So then the area of my triangle with A, B, and C as vertices is going to be 1/2 the magnitude of my cross product. Okay, because I've cut, that diagonal cuts that parallelogram in half. Okay, so let's calculate our cross product. We'll take the magnitude and we'll cut it in half, and that will give us the area of that triangle. Okay, so that's, I need to go, let's write it out here. So B1 cross B2, take the magnitude of it. Actually, let's just do, whoops, sorry. Sorry about that. Let's just do our cross product first, and then we'll take the magnitude. We'll do our cross product first, get the vector, and then we'll take the magnitude. Okay, so remember, cross product I, J, K, my unit basis vectors, which are going to force my answer into the form of a vector. So V1 goes first. So V1 is 1, 1, minus 2. V2, minus 1, 3, minus 1. And because I'm taking the magnitude, it's not going to matter if I go V1 cross V2 or V2 cross V1. I'm going to take the magnitude of it. Okay, so remember, our cross product I times first row, first column. I ignore those and I build up a matrix of what's left over. Minus J, first row, second column. I ignore those and I build up a matrix of what's left over. Plus K. First row, third column, I ignore those and I build up a matrix of what's left over. Okay. All right, let's go ahead and do it. Remember, we're going to multiply on the diagonals. So I have to cross these. I'm going to multiply, cross product these. Okay, I'm going to subtract out those values. So now this is going to look like I times, I'll do it out, 1 times a minus 1 minus 3 times a minus 2. That's my I. Minus J is going to be 1 times a minus 1 minus 1 times minus 2. It's always this diagonal minus that diagonal. So watch your negatives, right? I've got negative, negative, negative. Plus K, right? This is going to be 1 times 3 minus 1 times 1. Running out of space. Okay. Let's go ahead and do it. So this is going to be minus 1 minus a minus, so plus 6. This is going to be minus 1. This is going to be positive, negative, so minus 2. 3 minus a minus 1, so 3 plus 1. This is I times 5 minus J times a minus 3 plus K times 4. Okay, which I can put into vector form as being 5. Don't forget negative times negative, positive 3, 4. So this is my v1 cross v2. That's the vector that's normal to both of those. So we'll draw that out in a different way. It's going to look like, so here's v1 cross v2. Actually, that's v2 cross v1. v1 cross v2 goes this way, but it doesn't matter. Okay, so now we're going to take the magnitude, v1 cross v2. Okay, so magnitude, remember, means I take each component of my vector, I square it, sum it up, and then take the square root of it. That's how I calculate my magnitude. Okay, so taking this is going to be 25 plus 9 plus 16, taking the square root. Okay, when I add all those up, right, I'm going to get this is equal to radical 50, which you can leave as radical 50 or if you want, or you can simplify it. We'll simplify it in just a minute. Now, this is the area of parallelogram. And we want the area of the triangle is 1/2 the area of the parallelogram. Okay, oops, sorry. Which is going to equal to 1/2 times radical 50. Okay, which means I can also simplify. So radical 50 is 25 times 2. So this is 1/2. I'm going to leave it like this, but I'm also showing you, so it's 1/2 times 20, radical 25 times radical 2, so that's 5 radical 2, which I can write as 5 radical 2 over 2. They're equivalent. I will take either one. I don't care. Don't give me a decimal. They'll leave things in terms of radicals. See, that's the area of my triangle. I'll put that in red because it's the area of the triangle. Okay, so this is our area of our triangle. Okay, part A, part B, calculated the equation for the plane, the vector equation for the plane. We're going to talk about how to use cross product later, 1.5. Cross product to calculate the regular implicit equation for the plane. Right now, vector equation for the plane, area of the triangle spanned by these 3 points, has these 3 points as vertices. And now part C says, what's the angle between the 2 displacement vectors? Let's do that here. C, angle between 1 and 2. Okay, so we want to be able to calculate that out. Okay, so let's go ahead and do that. So that means, remember our description of our cross product. The magnitude of the cross product was equal to also, we built this up, it's the area of the parallelogram, so base times height, right? So V1 times V2 magnitude times the sine of theta. This is the angle between them. So I've got V1, V2, and I have an angle between them, theta. That's what I'm looking for. So I'm going to divide both sides by the magnitudes, right? And then I'm going to get V1 cross V2 magnitude divided by the individual magnitudes. And that's equal to the sine of theta. Now I have to take the inverse sine on both sides in order to find theta. So theta equals inverse sine. This is a button on my calculator. Right, my sine function and my inverse sine. See, sine minus 1. It's right above my sine function. Same thing for cosine. Okay, inverse sine of this whole thing here. So magnitude of my cross product divided by the individual magnitudes. Okay, and I don't care if you give it to me in degrees or radians, but you must tell me your units. Okay, we'll do both. All right, so when I do this, this is what I'm going to be filling in. So when I do this, I like to prefetch and figure out what are my magnitudes of my individual vectors. The magnitude of V1 is going to equal to, I've got 1 squared plus 1 squared plus a minus 2 squared. Square rooted. Watch out for your negatives, right? This should be minus 2 quantity squared. Make sure your calculator, if you put in minus 2 squared, my calculator would give me -4, and that'll be wrong. This is 1 plus 1 plus 4. Okay, so use parentheses when you're doing these out. So this is going to be radical 6, magnitude of V2, minus 1 squared plus 3 squared plus a minus 1 squared. Get in the habit of using parentheses so that you can keep track of the negatives. This is 1 plus 9 plus 1, which is radical 11. Leave it in terms of radicals. Don't simplify in terms of decimals because you'll get rounding errors, which will build up. Okay, so we did this. The magnitude of the cross product we said from before. This is from before. Was it part B? Okay, so I'm just going to pull that in from part B. Okay, so now I'm going to plug them into my inverse sine equation, right? So I'm going to say inverse sine of radical 50 all over radical 6 times radical 11 is equal to theta. Now, be careful, watch your parentheses, right? So these, I put little mini parentheses here. When I do this on my calculator, right, I'm going to get the big parentheses. So I'll go radical 50. Make sure you move out of your radical, right? This happens on my calculator. Move out of your radical, divided by parentheses, radical 6 times radical 7. Close parentheses equals, okay? And theta is going to equal to, I'll give it to you both in radians and degrees, 60.5 degrees or 1.056 radians. Like I said, I don't care which form you want to give it to me in radians or degrees. Either one is totally fine, but you must tell me your units because I need to know. Are we dealing with 60 radians? That's very different than 60 degrees. Okay. All right. So that's our cross product. I just want to give that's the last example, but I just want to give one last note. What does it mean if I have, we've been doing IJK inside of our cross products, but what does it mean if I have 3 vectors that I'm trying to do a cross product of? Okay. So let's just write this down. One last note about chapter 1.4. So we talk about our cross product, 2 vectors. It's basically a 2-dimensional procedure. Hang on a sec. It's a 2-dimensional procedure. Okay, which basically looks like, right, I've got my plane. Okay, and I've got, here's B, here's W. They're both on the plane, right? And then when I take the cross product, here's W cross B, and that's perpendicular to the plane. We're going to exploit that perpendicularity later in chapter 1.5. Okay, but if I, because that's right, if I do, I set it with I, J, K, and then I do the rest of my B and W vectors, okay? But now, if I do a cross product with 3 vectors, so instead of I, J, K, which is going to force my answer into a vector form, I'm going to use 3 vectors, right? It's called a triple product. And then what results is the volume of the prism that's spanned by those 3 vectors. Give me a sec here. That's spanned by those 3 vectors. So let me draw out what that looks like, right? So if I have a prism, and I say prism, but a prism is a 3-dimensional parallelogram. So this is a 3-dimensional parallelogram, and it looks like this. Let me see if I can draw this. Okay. So here's my parallelogram. Right, and it comes down. Okay, so here's my 3-dimensional parallelogram. This is a prism. Okay, now our 3 vectors in this case are going to be, here's my first vector A, here's my first vector B, here's my third vector C. Okay, so those are the 3 vectors that describe my parallelogram. Okay, so when I go to take the cross product of these 3 vectors to get the volume of the shape, I take the magnitude of A cross B cross C, and I'm going to get that. So this is basically the magnitude, which is the absolute value of our determinant. Okay, and it was going to give you a scalar, right? Your volume is just a number, it's a scalar. Okay, it's just going to give you a scalar, okay, which is your volume. Okay, of this whole shape right here. Okay, I could work through an example, but I think we already kind of talked about a determinant in 3 dimensions and what that looks like. Absolute, in this case, this is taking the magnitude of the determinant. In this case, this just means taking the absolute value of our determinant, because volume is always going to be positive. Okay, so just so you know, it is totally possible to take a cross product with 3 vectors, and what it actually means, geometrically speaking, is that we're doing the volume of the 3-dimensional parallelogram. We're not necessarily going to be doing this in class, but I just wanted to make sure that you guys had that, so that wasn't like some kind of an empty, you know, an empty spot in your mind about like, is this possible? Anyway, all right, so that's 1.4, finishing up. So what I'd like to do actually is take a break on 1.4, and you know, we're not going to start 1.5 today. What I'd like to do is I'll start 1.5 on Wednesday. We'll do 1.5 Wednesday and maybe part of Thursday. And I'd like to actually work through some of the classwork problems that we have for 1.3. And we also have a classwork problem set for 1.4, okay? I want to work through these things here just so that you guys can see these things worked out and what do they look like. And then we'll start just working it through. So these are dot products, these are projections, these are determining whether they're orthogonal or not. So I'll just start working through these problems, and it was requested that I keep recording when I do this, so that people who are logging in later can see you know, classwork problems worked out. So I'll keep recording. So keep that in mind if you want to ask any questions. If you don't want to ask questions or have your questions be recorded, you're welcome to come to office hours and then ask me about classwork or homework problems. Okay, so get out my notes. And we'll just start working through these things here. This kind of looks like one of our quiz problems here, where we had to add up our vectors. So that's kind of a review. I think maybe I'll skip that part and then go on to other problems. Okay. So I want to find the projection of B onto A. So first thing I want to do is I want to reduce that down to into its what these are as vectors. So I'm going to rewrite these. Remember our formula for projection here. This is chapter 1.3, remember, was dot product. So we're kind of taking a step back to remember how we did stuff. Remember our dot product, we multiply corresponding components together and we add them up. Leave my answer like this, or I can distribute this scalar. This is my scalar part. Remember, our dot product gives us a scalar. I can distribute that to all of my terms. So 15 times minus 3, 15 times 2, 15 times minus 2. These are equivalent. They're both acceptable answers. I'm just going to keep working through this classwork problem. I'm hoping that you guys are working on this also at the same time, so you can compare your answers to mine. Okay, so I'm going to use the dot product to determine if these are orthogonal, because remember the dot product is equal to 0 when the two vectors are perpendicular to each other. Okay. We'll take the dot product. The dot product is negative, so these two are not orthogonal to each other. They're not perpendicular. Dot product came out to be 0. This is kind of a funny one because this is actually the 0 vector. So this is like basically saying this vector here is perpendicular to the origin. So it's kind of funny. We don't think about the 0 vector as being a vector, but for mathematical purposes, we would think that they would be. Okay, so here's a case of two vectors that are not the 0 vector, two vectors. When I take the dot product, I get they're equal to 0, which means that they're perpendicular to each other. It's two dimensions, 3 dimensions will do 4 dimensions. The dot product will scale up to as many dimensions as we want. So I won't be able to draw them beyond 3 dimensions. There's another one that's a 4-dimensional vector that's also perpendicular. Find the vector component of u along A is another way of saying what's our projection of u onto A. Then this is the orthogonal component. So this is the orthogonal component of u on A. And then to get the orthogonal, I'm going to subtract my vector that I'm projecting onto, the projection vector from that. So here we go, look, so here's, these two are actually orthogonal to each other. So this is going to give me a 0. So my projection is equal to 0. So then the orthogonal component is just equal to u minus 0, which is equal to u. So think about it like this. Here's the u vector. U vector, here's our a vector, right? And since they're orthogonal to each other, which we just showed from the dot product, I can't, when I project it, I'm just projecting down to this tiny little point which has a magnitude of 0. And then the orthogonal component is u minus 0. The orthogonal component is equal to u, which we just showed here. So again, we're going to do it here. This is 4 dimensions, which I can't draw out very well. Okay, so there's my, I can simplify this. I can divide both by 2. This just becomes 16 divided by 13, minus 16 divided by 13, 1, 0, 5, which I can multiply through. I'm going to need to multiply through in order to calculate out the orthogonal. Okay, so I'll calculate out. Sorry, you can't see what I'm doing. I have to find common denominators on here. So 13 times 3. And 7 times. Okay, so I'm just adding things up. So 39 plus 16 is equal to 55, 13, because it's minus a minus. So watch your negatives. The 13, so this is 1 minus 0, so this is still 1. Minus 91 plus, minus 80. So minus 91 plus 80 is just going to be minus 9. This is my orthogonal component. Okay. Phew, it's a lot of classwork problems. Okay, so that's classwork there. Okay. All right, so let's try, I'm moving on to the other dot product page. It's the other dot product page. So again, I've got my A, B, and C in terms of my unit basis vectors, but I'm just going to rewrite them because I like them. Minus 3, 2, minus 2, B is equal to minus 1, 2, minus 4. Remember, it's just the coefficients. C is equal to 7, 3, minus 4. So A dot B plus C, so this is going to be minus 3, 2, minus 2 dot B plus C. So this is minus 1, minus 4 plus 7, 3, minus 4. The dot product is more expensive than addition in terms of computational stuff. So what I'm going to do is I'm going to combine these two here, and then I'll take the dot product. So minus 1 plus 7, 2 plus 3, minus 4 plus a minus 4, minus 8. So now I'm going to take the dot product here. So this is going to be minus 18 plus 10 minus minus, so plus 16. So minus 18 plus 16 is minus 2 plus 10. It's going to equal to 8. So that's our dot product. A plus B dot C, we're going to do that. So it's going to be minus 3 to minus 2 plus B minus 1 to minus 4 dot C 7 3 minus 4. So when I combine these, right, I'm going to get minus 3 plus a minus 1 minus 4. 2 plus 2 minus 2 minus 4 minus 6 dot here 7 minus 4. 4 times 7. Remember, corresponding components get multiplied together and we add them up. Plus plus plus. So minus 28. Okay. Plus 24 gives me minus 4. This is minus 4 plus 12 gives me 8, which we would expect these to be the same, right? Because dot product, right, I can group things out differently. It's like I'm gonna, you know, add those together. Okay. Which of the following vectors is a possible value of v? I guess I'm taking the magnitude again. So I'll just take the magnitude of each. So 1 squared plus 4 squared plus 0 squared, which is equal to 1. This is 1 plus 16 radical 7. So that doesn't look like it. Let's try this one. Minus 1 squared plus minus 2 squared plus 0 squared. So this is 1 plus 4 radical 5. Let's try this one. 2 squared plus 3 squared plus 3 squared. This is 9 plus 9 plus 9, which is radical 27. This one is 2 squared plus minus 2 squared plus 1 squared. Right, this is 4 plus 4 plus 1, which is radical 9, which is equal to 3. So that's this one. We did this already. So if u equals this and the magnitude equals that, then what is k? So let's talk about how do we calculate the magnitude. That's going to be 1 squared plus k squared plus a minus 2 squared plus 5 squared, right? And I do square root. And that's equal to 6. We were told that the magnitude of u is equal to 6. So now I'm going to add these up. So this is 1 plus k squared plus 4 plus 25 equals 6. So I'm going to add them up. So I'm going to get k squared plus 1 plus 4 is 5 plus 25 is 30 equals 6. Now I got to get the k out of my radical, right? So I need to square both sides. I'm going to get k squared plus 30, right? Because the square of a radical just eliminates it, equals 36. So now I'm going to subtract 30 on both sides. K squared equals 6. Sorry, you can't see what I'm doing. Now I'm going to take the square root of both sides. So k equals plus or minus radical 6. Plus or minus because I'm going to square it inside here, so it isn't going to matter right, if it's positive or negative. Everybody see how we're doing this? All right, I'm going to do chapter 1.4, classwork problems. So find the vector and parametric equations of the plane that contains the given point and parallel to the two vectors. So here's our point, vector, vector. So remember our plane equation. Okay, so this is just simple. I'm just going to substitute in each of these. So x bar equals my point, minus 3, 1, 0. Oh, sorry, plus t1 times v1, 0, minus 3, 6, plus t2, minus 5, 1, 2. So there's our vector equation. As parameters, I can break them down into x component is all just my all just the x components. So minus 3 plus t1 times 0 is just 0 minus 5 times t2. Y equals my y component, y minus 3 times t1 plus 1 times t2. My z components are 0 plus 6 times t1 times t1 plus 2 times t2, all the z components. So just broke it down into individual pieces. And then I'm gonna run out of space here. So let's I'm gonna I'll try these. I'll do these down here, and I'll start down at the bottom, and then I'll work on the other page. So part A says V cross W. So I'm just gonna start working it through. Okay, so notice you can see on A and B, so A was B cross W, and B was W cross V. They're the same components, but negative, right? So this is positive 32, negative 6, negative 4. This is negative 32, positive 6, positive 4, right? It's just like what we talked about in class, but give us a clue. So V dot V cross W. Okay, so let's fill in the blanks. So V 0, 2 minus 3 dot, and V cross W we just solved for that. So V cross W 32 minus 6 minus. Okay, so I'm plugging in the answer from before. I'm going to take the dot product here. Okay, which makes sense. V was one of the components of our cross product. We would expect the cross product to be normal to the input value, and our dot product on two normal vectors is going to be equal to 0. Nope, that was D. Sorry. Change that to D. C says U plus V cross W. Okay, so let's write this out. So I'm trying to remember, what are U? 3, 2 minus 2. V was equal to 0, 2 minus 3, and W was equal to, W was 2, 6. Okay, so u plus v cross w. So u plus v plus v cross this one, 2, 6, 7. So I'm going to add first, and then I'll take the cross product. So 3 plus 0, 2 plus 2, minus 1 plus a minus 3. And I'm going to cross it with 2, 6, 7. Okay. So I'm going to set up my cross product. Okay. This is positive because it's minus 24, so it becomes plus 24. And the same thing here. So minus a minus, so minus, subtracting minus 8 becomes plus 8. No, so these are both positive, so I subtract right here. Then I have to distribute this negative to this term here, 29. Okay, so let's see, that's D, we just did D. E says V cross V. See what that looks like. Okay. All right, so I'm going to do the same thing. Okay. So remember, this is minus a minus 6, it becomes plus 6. Makes sense, right? Remember how we said the cross product, if I take the cross product of two vectors that are parallel to each other, right, it's based on the sine of the angle between two parallel vectors is 0, sine of 0 is equal to 0. So we expected to get a 0 out of here. It's good that we're just showing it. So v cross v is equal to 0. Okay, what was f? U minus 3w. Cross u minus 3w. Okay, so I don't even need to do this one. U minus 3w. Right, this is a linear combination, but watch what's going to happen. We'll prove it to ourselves, but I'm going to have the same vector on each, and I'm going to cross product those same vectors. I would expect to get a 0, but let's do this. So this is u minus 3w. So u minus 1 minus 3 times 2, 6, 7. This is going to be, so this is minus 6, 18, 21. So this is going to look like 3 minus 6 minus 3, 2 minus 18 minus 1 minus 21 minus 22. Okay, so you're going to get this, it's the same thing here. Let me just make sure I wrote it down right. Okay. And the cross product of a vector by itself is just equal to 0, 0, 0, which is our 0 vector. Okay. 1.3, 1.4 classwork all worked out here. Okay. You guys have any questions at all before we sign off? If you want, you can ask me questions in office hours today at 1 o'clock. Otherwise, I hope you guys have a great day today. Bye.